All right, here we go. So, as I alluded to, that is a horrible sentence, at the end of the last video, today we're going to be talking about rolling. So what happens when a thing rolls? So the idea is that, you've got this wheel that's rolling through space. There's a little point on the wheel, right? So as I said at the very end of the last video, the idea is, as it rolls, it is moving translationally or linearly, right? But it is also moving angularly, right? And so the motion as our thing rolls, unfortunately this program won't let me both rotate and move at the same time. But the idea is because it has both of those two types of motion, it's got two types of energy, right? It's got kinetic energy because it's moving, so that's 1/2 mv squared, where v is the velocity of the center of mass, right? But it's also got rotational kinetic energy, which, as we learned in the last video, is 1/2 times I omega squared, okay? All right, so there's a little bit of a trick to that. So anyway, this is sort of where we're headed, all right? So like I said, so the idea is as this thing moves, we've got both rotational motion and translational motion combined to give us rolling motion, right? Okay, so notice that what's sort of at the heart of this idea of rolling is that as long as a thing is smooth rolling, and we talked about smooth rolling last time, it turns out that the velocity of the center of mass is equal to the angular velocity of the object multiplied by the radius, okay? And you can see that here, right? That, if your object is rotating with some angular velocity, here's your radius, right? So this point at the outside edge has a velocity of, that's, v, and this guy has a velocity that's v. Relative to the ground, we know that this point isn't moving, okay? And the only way that can be true is if the object is rolling forwards at a velocity that cancels out this velocity, right? So long story short, and this should make some sense, right? That the center of mass is moving with the wheel, so the velocity of the wheel is the same as the velocity of the center of mass. So there you go, all right? So that's what's sort of at the heart of this thing, all right? And I guess worth noticing, and this really isn't going to be as relevant this chapter as it was last chapter when we were doing torque, but the acceleration of the center of mass is alpha times r. Okay. All right, so our thing, our wheel, or our whatever our circular object is, as it rolls, has both rotational motion and translational motion, okay? So what that means is that it has two types of energy, all right? So everything is here kind of already worked out for you. But I'm going to add in a slide here. Let me just kind of work you through this thing, okay? So imagine a thing rolling, all right? So imagine that our thing has a rotational inertia of beta times mr squared, where beta is some fraction, right? So maybe it's a disk, so beta is 1/2, or maybe it's a sphere of some sort, so beta is 2/5 or 2/3 or something, all right? So here's our thing rolling along, all right? And it's moving with some velocity. All right, so what that means then is the kinetic energy of this thing as it rolls is going to be 1/2 times m times the velocity of the center of mass squared, okay? But it's also got some rotational kinetic energy, right? Because in addition to moving translationally, it's also moving angularly. And so that rotational kinetic energy is 1/2 times I times omega squared, right? But let's do two quick substitutions, and this is huge. Being able to understand this and reproduce this little calculation that I'm making here will make your life easier, okay? Well, at least your physics life easier, okay? All right, so here we go. So this is 1/2 times, I'm gonna replace I with this, so this becomes beta times mr squared times omega. Oh, well, remember, omega is the velocity of the center of mass over the radius, right? Aha. So I'm going to replace omega with v over, capital R, and square it, right? So this is just v squared over r squared, and once again, these r's cancel. And so what I end up with is beta times 1/2 mv squared. Right? So what that means is if your thing is rolling, if an object is smooth rolling, then your rotational kinetic energy is just beta times whatever your kinetic energy is, right? That is super useful. If you've got an object that is rolling, your rotational kinetic energy is beta times kinetic energy, or just as useful, it's beta times 1/2 mv squared, okay? We're going to use that again and again and again, okay? I guess if you wanted to extrapolate this one more step, you could do this. You could go, oh, well, total kinetic energy is kinetic energy plus rotational kinetic energy, right? So that's kinetic energy. I'm going to put a 1 in front of it. This is 1 times kinetic energy plus beta times kinetic energy. And then if you factor out KE, you get 1 plus beta times KE. Okay? So honestly, in problem solving, for whatever reason, I don't find I use this as often as I use this. Largely just because I'm worried that if I ever did this on an AP test, the AP graders would be like, where did you get that? Okay? Because weirdly, this little trick here is not a thing that I see in books a lot, even though it comes up a lot in problem solving. Okay? Which is why I say it's probably not a bad idea to understand this. And in case you need to use this little trick on an AP test, that you're able to sort of derive this result. Okay? All right, cool. Well, let's see if we can apply this to a thing. All right? So let's imagine an object with a rotational inertia of beta times mr squared rolling down a ramp that's 4 meters tall. Let's find the velocity at the bottom. All right? So here's our ramp. The height is 4 meters, so up the top, our height is 4 meters. It's going to roll from rest. I did not explicitly say that. So let's assume that up here at the top, the velocity is 0. And the question wants to know, when it gets to the bottom, what is the velocity? Okay? So it turns out we can use conservation of energy to solve this. And why is not at all obvious. Okay? Because the weird thing here is, remember, in order for a thing to roll, we have to have friction, right? Because if there's not any friction, so here's our ball, just put a little dot on it and mark a spot on it. So remember, if there's no friction, then the ball, oops, if there isn't any friction, then the ball will just slide down the ramp, okay? You have to have friction in order to get it to roll down the ramp. Again, I can't roll it and move it at the same time, but so, all right, so we do have friction. So the weird thing here is the ball is going to move down the length of the ramp, however long the ramp is, and friction is going to push up, and so it seems like you ought to just be able to do work as force times distance. But when an object is rolling, the friction does not do work. It merely determines whether the kinetic energy is linear or rotational. Here's why. Let's go back to that analogy. I don't know if you remember when we originally learned about rolling, I told you that we could think of an object that's rolling as being an object that's kind of perpetually tipping over that pivot point, right? Remember I said, oh, what if it's a cube rolling over, right? So the idea is at the point of contact, here's my friction, right? Maybe friction is preventing this thing from sliding. You know, maybe you're pushing it, causing it to roll over, and friction's preventing it from moving. The idea is at this point of contact, there is no displacement. So when you calculate the work done by friction, it's your force of friction, which is whatever, times your displacement. So friction is not actually doing any work, all right? The only thing friction is doing is it's determining whether the energy gained by the box, when you know, in this case, you're pushing it, right? And here's the force of you trying to tip this thing over, right? Because you're producing torque here, you're giving it rotational kinetic energy, right? If there was no friction, then it would just become linear kinetic energy, okay? But friction is not actually doing work. It's just sort of determining where that kinetic energy goes, okay? Whether it goes into linear or rotational kinetic energy. Okay? That is big. Please make sure you know that idea is so important that I'm going to draw a hollow smiley face. He's very happy. Well, I'm actually pretty happy with that. Let's put hands on him. Ah! And a hat and feet. Okay. I'm sorry that you were exposed to that. Okay, so there's our object. All right, so it's going to roll down the ramp. So what forces are on it? Well, let's see. Let's go through this and actually make our free body guy here. So let's see. So you're going to have your force of gravity, which is a conservative force. So that doesn't change the total energy. You're going to have a normal force, which goes through your pivot point. And you're going to have friction, which, as we just said, does not do any work. So that means our total energy is the same. So that means that the total energy at the top of the hill is equal to the total energy at the bottom of the hill. So here we go. Let's solve this thing. All right. So up the top, what type of energy do we have? At the top, we've just got gravitational potential energy. And then when we get to the bottom, the gravitational potential energy is 0, but we've got kinetic energy at the bottom, and we've got rotational kinetic energy at the bottom. Okay, so the GPE at the top, well, that's mass times 9.8 times the height. Do you know what? Well, yeah, all right. That's equal to the kinetic energy at the bottom, 1/2 m times v squared, plus the rotational kinetic energy at the bottom. Oh, we determined that that was beta times the kinetic energy. Okay, so this, as we have said, is just 1 plus beta times the kinetic energy equals mass times 9.8, oops, times 4. And I am happy because I noticed that these m's cancel. So I can multiply by 2, divide by 1 plus beta, and then take the square root, and I will have my velocity. So the velocity is going to be multiplied by 2, so you're going to get 2 times 9.8 times 4, so that's actually 88.2 if you're keeping score, divided by 1 plus beta, square rootified, and there is your velocity. Cool? Well, the reason I hesitated, I was wishing I just left this as h. This top part is just 2gh over 1 plus beta, square rooting. Notice, as we have learned, a couple things. One, the angle of the ramp doesn't matter, right? Because you're still converting the same amount of gravitational potential energy to kinetic energy. And secondly, as your beta goes up, your velocity goes down, right? Because as you have more rotational inertia, it's going to be more resistant to rotating, and that's going to slow it down. Okay? So those are two things to notice. All right? So here's a concept-y question. Oh, no, here's a fun start. Here's a concept-y question. Disks A and B are identical, and they roll across a floor with equal speeds. Then disk A rolls up an incline, reaching a maximum height of h, and disk B moves up an incline that is identical, except it's frictionless. Is the maximum height reached by disk B greater than, less than, or equal to h? All right, so let's draw. Here's disk A. So disk A is going to roll. Here it is. Here's our disk. All right, so it's rolling along at some velocity. So it's got a velocity. The height here is 0. So this is going to determine the kinetic energy it's got at the beginning, right? It's also going to determine the rotational kinetic energy it has at the beginning, right? Now, as it rolls up the ramp, it's going to slow down and eventually stop, right? Now, remember that it's smooth rolling, okay? And we've got friction. And since it's smooth rolling, that means V is omega r. So when it gets to its highest point, both my velocity and my angular velocity are going to be 0. So that means now all of my energy is gravitational potential energy, right? So all of this total energy became converted to GPE, right? So that is disk A. Now, disk B, let's think about what's happening with disk B. Here's disk B. No friction. Okay, so here it is. It's down at the bottom. It's got the same velocity, therefore it's going to have the same RKE. It's going to have the same KE. As a result, it's going to have the same total energy as wheel A had, right? So if I call this the total energy of A, then this total energy of B is equal to the total energy of A, right? Because they're identical, all right? But the difference is now, because there's no friction, there's not going to be anything, it's not going to be smooth rolling anymore. There's not going to be anything to slow down the rate at which the wheel is rotating. So the idea is when it gets to its highest point, it won't have slowed down, right? And as a result, we're still going to have all the rotational kinetic energy we had before and some GPE, okay? But the idea is here, all of the total energy becomes GPE. Here, it's just the kinetic energy that becomes GPE. The rotational kinetic energy doesn't change. And as a result, the height here is less than h, where over here the height is h. Okay? All right, because here, in the second example, you're not converting that rotational kinetic energy to gravitational potential energy. Only the kinetic energy gets converted. All right? Here's another way of thinking about this. All right? Let's think about our free body diagrams. And this is wild. I remember the first time I saw this, I was like, what are you even talking about, Mr. Physics Professor? Okay, so here's our wheel rolling. This is wheel A. We've got friction. So as it rolls up the ramp, let's see. So we got gravity. We've got our normal force. Right? And so our net force, let me split up gravity into components. So I'm going to split gravity up into components. So here's our FG perpendicular. That's not really going to affect anything. We've got our FG parallel. All right, now think about this. All right, so if I consider the center point as my pivot point for a minute, and I imagine the wheel spinning this way, as it rolls up the hill, do you agree that it's slowing down? Yes, I do, Mr. Hecker. Oh, cool. So if it's spinning this way, the only force providing torque is the friction down here, right? So if you've got a wheel spinning clockwise and you want to slow it down by applying a force at the bottom, don't you have to push it up? So this is wild. When you roll a ball up a hill, the friction goes uphill. It works against gravity. And so what ends up happening is, because you've got friction here, you've got a smaller net force pulling down the hill, and so it takes longer to stop, okay? Without friction, then you've just got gravity, okay? So here, in this drawing, our net force is less negative. And so the acceleration is less negative, and so it takes more time to slow down and stop. Okay? So, that's a good exercise there to think about that, about the fact that that friction is always up the hill. Okay? I think that's gonna, as long as you're just talking about free rolling, that's gonna always be true when you've got a thing rolling on a ramp. The friction is always uphill. The only difference would be if it was like, you know, if there was a third force on it, you know, that might change it. Okay? I think that's it. It is another short video. Cool. All right, so problem solving, this is your jam. When you're solving problems on the homework, you're going to use this trick here, where you replace your rotational kinetic energy with beta times the kinetic energy. Okay? That's it.